there are a lot of things about the universe that I find it almost impossible to imagine. Well, actually impossible to imagine. One's just the size and scale of it. I mean, in the piece of the universe we can see, there are something like, roughly, 2 trillion galaxies. We haven't counted them all, but that's an estimate based on surveys of the local universe. 2 trillion, 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy. And there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it. It is impossible to visualize the scale of the universe. So that's the first thing. I could then list a lot of more things, but we'll stop there for now. But just the size and scale of it, I think, is beyond imagination. What does it mean to live a finite, fragile life in an infinite, eternal universe? Which I think is the only interesting question, actually. And it's a question that is raised powerfully when you consider the size and scale of the universe. That's a question about the human experience of life. And if you think about everything, like you said, movies, music, art, for back hundreds or even thousands of years, most of it has been about that question. It's about dealing with what it means to be human. So I don't think there is any separation at all between anything that we could talk about, be it movies or literature or art or whatever, and science. They're not separate. They're all things that we do as humans to try to understand what it means to be human, ultimately, I think. So therefore, whatever you ask, it clearly is about that, I think. The way I look at life is that it's the most important phenomenon that exists in the universe. Without life, the universe is, by definition, meaningless. It's clearly, but meaning enters the universe with consciousness. And consciousness is a property of living things. And so, without living things, there's no meaning. So I think that, let's flip it round. If this is the only planet in the Milky Way galaxy that currently hosts an intelligent civilization, then it's the only island of meaning in a sea of 400 billion stars. And therefore, we have a tremendous responsibility to protect this island of meaning. If we mess it up, we will be responsible, if that's the case, for annihilating meaning, perhaps forever, in a galaxy. So I think life's important. Life is a different thing. That's why we're careful, and rightly so, about exploring Mars, because there might be Martians, right? Not things with loads of legs and things, but microbes. But even so, if they've been there, if there's a separate genesis of life on Mars, then that's a tremendously valuable thing, and we should think about it very carefully. If there are no Martians, build cities on it. Yeah. I'm sure there's life out there, and civilizations out there. I mean, there are, the piece of the universe we can see, there are of order 2 trillion galaxies, in the observable universe, which is a small patch of a possibly infinite universe beyond. So there's definitely life and civilizations out there. There has to be. But the question really is, how many of them are contactable? How far away do you have to go? And it could be you have to go out of our galaxy to get another one. So I think that's the real question. It's internal to our galaxy. Because I don't see we're ever going to be contacting things from another galaxy. I just think the distance is too big. So it's practically, it's almost irrelevant. But inside our galaxy, 400 billion stars, then that's the question. What is there in there? So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty, and expanding extremely fast. And that expansion slowed down and stopped, and the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. So that's textbook. It's a textbook theory called inflation. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky. Because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea. And that theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever, and it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, and then it slows down and stops in little patches, and each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse. And it answers some neat questions, that, because if you say, why is our universe the way that it is? Why are the laws of nature such that life can exist, for example? Well, the answer might be that all possible combinations of all the laws of nature exist in the inflationary multiverse. So then it's not surprising there are universes that permits things like us to exist, because every possible universe exists in the inflationary multiverse. And that's a well-supported theory. It's a theory, so this is not the same as saying there was a Big Bang, which we know. This is kind of, what's a theory? It's a guess, basically. But it is a theory that in its simplest form has made predictions that have subsequently been verified. And we could go on then. There's the so-called many worlds interpretation of quantum mechanics, which is more kind of Marvel film kind of multiverse, where so quantum mechanics it's a probabilistic theory. So imagine a quantum coin, I call it. And the quantum coin it doesn't have to be heads or tails, it can be heads and tails. So it can be mixed up. It can be both heads and tails at the same time. You might have heard of Schrodinger's cat, which is a cat in a box, and it's both alive and dead until you observe it or interact with it in some way, and then you find out which one it is. But before you looked at it, or before you interacted with it, it was both. I say sometimes in my live shows, it's kind of a joke, right? So I'm not insulting philosophers here, but I say, there's only one interesting question in philosophy, right? And I don't really mean it, but I think it sounds funny. So the interesting question is, what does it mean to live a finite, fragile life in an infinite, eternal universe? So that's not that funny, right? It's a good question. What does it mean to live a finite, fragile life in an infinite, eternal universe? And I think the answer is that, sort of paradoxically, whilst we are definitely physically insignificant, I've just said that the Earth is one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in a small patch of the universe, right? So we're definitely small. We can't argue with that. We're just specks of dust. But if you think about what we are, so everybody, me and you, everybody, we're just collections of atoms, right? Some of them are as old as time, pretty much, and some of them were the other ones. Everything else, other than the hydrogen in our bodies, was made in stars, right? So we're all cooked over billions of years. And we're in this pattern that can think. So suddenly, as the great Carl Sagan said, you have a means by which the universe understands and explores itself, which is us. And that sounds unlikely when you put it like that, that you can have a few things that were cooked in the hearts of stars. You stick them together in a pattern and suddenly it has some ideas and starts writing music and art and things. That's quite difficult to comprehend, right? But that happened here. We know that because we're sat here having a conversation. And so the question then becomes, well, on how many other worlds did that happen? And that's where I think the value can come in, because it's a reasonable guess. And it's just a guess, right? But it's reasonable. You can make the argument that there aren't any other worlds where this happened, certainly in our galaxy. So it could be that this planet, notwithstanding its physical insignificance, is the only place where anything thinks, right, for millions of light years in every direction. And suddenly, therefore, you end up considering this planet as being the most valuable place in the local universe, notwithstanding the fact that it's small. And that idea, it's not just a complete random guess, by the way. We've had a bit of a look. Astronomers have pointed radio telescopes up at the stars for a while, 50 years or more now, and heard nothing. We've seen no evidence of any civilizations out there beyond Earth, and that's a surprise. There's a reasonably plausible explanation for that, which is biology, which is that if you look at the history of life on Earth, then you see that life began pretty much as soon as it could here on Earth. We have evidence there was life 3.8 billion years ago, something like that. And the Earth's 4.5 billion years old, so pretty quick in geological time you get life. But then if you talk about advanced life, complex life, multicellular life, then there's no evidence at all back beyond a billion years. Actually, really, in the fossil record, 650 million years ago or something, you start seeing the first evidence of complex creatures. So that means that on this planet, it took over 3 billion years to go from a single cell life to anything more complex than a single cell. And then another 500 million years or so to go from the multicellular things to a civilization. So it's 3.5 to 4 billion years. It's a third of the age of the universe. That is a really long time. If you say that's an unbroken chain of life on a little piece of rock in a violent universe, and that chain was not cut for 4 billion years in order to get us. And that might be a big ask, right? We live in a really violent universe. You look at the Milky Way and you look at that arc of stars across the sky, 400 billion suns. All there will be up there at best is slime, just slime, nothing, right? And I think that's a reasonable guess. That's where I start from. I mean, I wouldn't be surprised if that's wrong. Then you go, okay, good, well, fine. But at the moment, it looks like there isn't anything else other than slime. We haven't even discovered slime, by the way, yet. We're still in the position where we've not seen anything, not even a single cell on Mars or the moons of Jupiter or somewhere like that. So at the moment, we are alone, as far as we can tell. I mean, we know that there are a lot of potentially Earth-like planets. I mean, I think the current estimate is of order 20 billion in the Milky Way. So maybe 1 in 20 stars or 1 in 10 stars, something like that. But that's potentially Earth-like, so rocky, the right distance from the star, possibly to have oceans on the surface if the atmosphere is right, and so on. And you might expect, and we don't know, but knowing what I know about biology and the history of life on Earth, you might expect some of them to have microbes on them. It doesn't seem so far-fetched, given that we know that life arose pretty quickly on the Earth when the conditions were right. There doesn't seem to be anything magical about the transition from geochemistry to biochemistry, which is what life is on a planet. But from the origin of life, it took the best part of, or even a bit more than, 3 billion years to go from the origin of life and some single-celled things to complex multicellular life. 3 billion years is a long time. It's a quarter of the age of the universe. And so that suggests, without knowing anything else, if you just have to guess, that suggests that the transition from single-cell living things to anything, something as complex as a blade of grass, never mind a human being, something that can build a civilization, is not as likely, right? Because it took I mean, you think, so from the origin of life on Earth to the first industrial civilization on the planet is 4 billion years, 3.8 billion years. If you ask the question, how many of those potentially Earth-like planets are stable over that kind of timescale, then the answer might be very few. So it's in that sense that I think I'm a rare Earth person. I think that if I was forced to guess, with the additional bit of evidence that we haven't seen any evidence of anything, so there isn't any evidence of advanced civilizations out there currently, then I think you put those seasons together and you think it's probably biology. I think the biology is the thing that stops it. There's a very good friend of mine actually in Manchester who's a professor of zoology, and he likes to say that all there will be there at best is slime. So it's probably a slime-filled galaxy, if I was to guess. I mean, no one would be less surprised than me if a flying saucer landed tomorrow, because I'd go, okay, that solved a problem for me, because it's a big mystery. It's like, why, with all this time and all this planets, does it seem that there's no big spacefaring civilization out there that's written its existence, the evidence of its existence across the sky? It's a problem. So I'd just tick it off and go, okay, that's good. So I wouldn't be surprised. People always have a go at me on Twitter and things like that for going, you're closed-minded, you don't believe in the flying saucers. I'm not closed-minded. I've thought about it very deeply, and it surprises me that there aren't any flying saucers, but I don't think we've seen any. So I'm very open-minded about the subject, but I just don't. I have seen not one scrap of evidence from any reputable source that tells me that we've been visited by aliens. You talk about that, the extraordinary claims require extraordinary evidence. So if you look at the search for life on Mars at the moment, so the Perseverance rover, it's got experiments on it, it's going around, it's taking cores, it's on its way to a river delta at the moment. It can drill, it can do chemistry and spectroscopy and all these things. But ultimately, every scientist I've spoken to on that mission said that even if we get signs that there's complex organics there, which we could gather from those instruments, the only way we will believe it is if we bring those samples back to Earth and we subject them to experiments with these huge facilities we've got here on Earth. And even then, it will probably take about 20 years before people accept it, because if you look at there are structures called stromatolites on Earth, right, which are now accepted as the oldest evidence of living organisms on the planet, 3.8 billion years ago, off the coast of Western Australia, for example. And those things were the subject of debate, even though we had them in our hands. For 20 years or more, people were arguing about whether they were evidence of life or not. So that's how hard you have to work when you've got small amounts of evidence from a long time ago, in that case, or a different planet in terms of Mars. You've got to work very, very, very hard to show that you've not been misled. And that's going back to all the way to Feynman again, the satisfactory philosophy of ignorance. A lot of science is what's called, in my field, particle physics. It's about errors. It's about quantifying the errors in your observations. What are the possible sources of error? What are it's like if you toss a coin 10 times, it might come up heads 10 times. Doesn't mean the coin's weighted. There's a probability that will happen. So you've got to make sure that you understand the probabilities and things. When you're looking for life beyond Earth, remember that even looking for life on Earth, if you go back 3.5 billion years, has been tremendously controversial because it's hard to show. So short of, very clear evidence of a UFO literally landing in like Hyde Park or something, then I'd go, okay. Or some signal we could receive, we look for it. We've got this SETI, which is I strongly support. It's a really valuable scientific endeavour to go and listen. I mean, the first thing you want to do is look for evidence of civilizations out there. So we do, and we haven't found any. We found a couple of little blips, and they don't end up being repeatable. So then we try to look for them again, they're gone, like the famous wow signal. So it's just the case that, There's an analogy I sometimes draw, which is that, we all get on aircraft, for example. Imagine getting on an aircraft. Imagine if they hadn't repeatedly tested it. Right, imagine if someone had gone, I think the wings should look a bit like this, stick them on, it'll be fine. Then imagine what that would be like, that experience. It's an example of how in certain things, in engineering, we take it for granted that someone's really careful. And it's good. When you build a bridge, you don't just go, I'd be all right. Just like the Golden Gate Bridge, just stick a few screws, it'll be fine. It's well tested. It's the same with knowledge, actually. So knowledge only becomes reliable knowledge when you test it. Like a bridge only becomes a reliable bridge when you test it. It's the same. So I encourage people to do that when they're just kind of guessing based on a fuzzy blob taken by someone on their 1990s phone. Just say, actually, imagine that the analogy is that this is an aircraft that I'm going to get on. And imagine if it's been subjected to an equivalent level of scrutiny. Well, yeah, so it sounds like science fiction, doesn't it? You say, well, we've all seen Hollywood films where asteroids come and don't look up, right? Brilliant film, I think, where an asteroid comes and we don't even believe it. So you see it and people don't even believe that things coming. That's real, right? We know that the dinosaurs, other than the birds, were wiped out by a big asteroid impact 65 million years ago. We know that. So occasionally big pieces of rock hit the Earth. And occasionally those big pieces of rock are big enough to cause mass devastation that easily take out a city, pretty easily take out a country, sometimes take out, like the one that took out the dinosaurs, take out pretty much every big living thing on the planet. That's happened before and it will happen again. Now, the big planet killer, so-called planet killer asteroids are very rare. I can't remember off the top of my head. It's something like 1 every 100 million years or so, roughly, you'd imagine. And we had one about 60 odd million years ago, right? But the little ones that can take cities out, there was one in Siberia in, I think it's 1908, I might be slightly wrong, but exploded in an airburst over Siberia and flattened an awful lot of forest. And if that had happened over a city, it would have flattened an awful lot of city. So these things happen. What we do now is we look for them quite sensibly. So we map the orbits of the big asteroids. We've got most of them, we think, that cross the Earth's orbit. And we monitor them all the time. And we have what's called a keyhole system. And it says that if one of these asteroids goes through this point in space at this time, then we're worried about it. And we'll be very careful and we'll watch it. So we're watching them. And if one goes through the keyhole, then what you need to do is nudge it a bit so it doesn't hit the Earth. And the DART mission was the first mission designed to make sure that if we really want to hit an asteroid with something, then we can do it. And it's hard. And so we did it. It was a very clever mission because it's a double asteroid system. So the little one of them was hit. So there's two of them going around each other. And we hit one of them. And that means that you can measure the orbit afterwards of these two things orbiting around each other to see how much we deflected it. So it's a smart thing to do. So we're really developing the technology so that if we have to hit a big one and move it away, then we can do that. I mean, there are things we couldn't do anything about. Comets are really problematic. So asteroids are pieces of rock. They're in orbit around the sun. There's the asteroid belt where there are lots of them. The comets are more like often described as icy snowballs. And they come from much further out, a place called the Kuiper Belt or the Oort cloud. So way, way out. Actually, the Oort cloud of comets extends probably about a quarter of the way to the next star, so it can go out a light year or so. So there's all this stuff around there, which are basically icy snowballs. And they, because of collisions and interactions in the Kuiper Belt and the Oort cloud, or even passing stars can disturb, just anything can disturb these things, and they can come and fall in towards the sun. And we saw one recently, Schumacher-Levy 9, relatively recently, which hit Jupiter. And we didn't see it coming until a few months before it hit, I think maybe a year or something. I think it was even quicker than that, maybe a few months, let's say. And it made a bit of a mark in Jupiter, actually, when it hit it. It was actually the hole it left was bigger than the Earth. So these things, they're big, right? And they come in and they're unpredictable. And we'd have a lot of trouble with one of those. So we'd have less trouble with the asteroids. At the moment, we'd have an awful lot of trouble with the comets. There's nothing we could do, actually. But it shows you though, doesn't it? We talked earlier about how long it takes to get something as complex as a human being on a planet. You've got to avoid that. And so we did, 65 million years ago or so, the dinosaurs were pretty much wiped out. And that left a little evolutionary niche for a little thing, shrew-like mammal type thing. And ultimately that's why we're here. If that hadn't hit and wiped out, cleared the way, we wouldn't be here. You probably wouldn't have a civilization, you would guess. And so, there would be none of the things that we just take for granted in potentially the Milky Way galaxy. So if we're the only civilization in the galaxy, then I think it's pretty likely that if that comet hadn't hit 65 million years ago and wiped out dinosaurs, there wouldn't be any civilizations in the galaxy. So nothing would know anything. So none of this knowledge would exist. So that just shows you how precarious the position of civilization and life is. Well, so the way that the Earth will end ultimately is as a cinder, right? It's because what's going to happen is that the sun, starting in a few billion years' time, actually, but it's going to start growing. It'll grow as it gets older, and it'll swell up. It probably won't engulf the Earth, but it'll get close. Right? The Earth will probably drift out because the sun will lose some mass. So but it'll toast it basically. So the Earth will end up toasted as a cinder, probably still orbiting the remains of the sun, which will be what's called a white dwarf star, which is just something that basically fades away. So that's what's going to happen in about 5 billion years. Well, that's what's going to happen. So that's how our world ends, as a crisp, basically a cinder. If you mean by the end of the world, you mean the end of civilization, then long before that, we'll have had to escape, because it will become the conditions on the planet will not support complex life like us. It'll be too hot. But the possibility is that we could destroy ourselves, which is it would be, given that it's quite possible that there is nowhere else in a galaxy, then, as we said before, that would be a really silly thing to do. So I think it's more likely. We might not have to wait for the sun to do it, because we might do it through our own stupidity. So we know that material is exchanged between Earth and Mars. We have Martian meteorites on the Earth. And we know that microbes can survive space travel. We know that they can exist in hostile environments like the International Space Station on the exterior, for example. So there's no reason at all where there couldn't have been a single genesis on Earth or Mars, and that life could have been transferred just randomly because the planets exchange material. So you've got to show that it's a different biochemistry. It's very hard to do, especially because you might have things like stromatolites, which are not really life at all. They're the products of life, right? They're the structural evidence of life, but potentially without the biochemistry. Because one of the ways you look for life in a rock is you look for it's not really looking for just the elements, the molecules and things. It's looking for how they're distributed, because life tends to clump things together and distribute things in interesting ways. The layers or concentrations of things, that's what life does. So the key thing that perseverance is not doing is grinding things up and putting them into a laboratory internally to see what's in there, because now it's much better understood, actually, that really part of the evidence for the life is how the structure of the rock has been modified by life. That's what we see on Earth. We see that that's one of the key smoking guns, actually. So it's hard to show that life exists. We think it probably does, otherwise we wouldn't be looking for it. again, when people say, "Oh, you're so close-minded, you don't believe in aliens," you go, "Well, actually, most people do think there's a chance of aliens. Otherwise, you wouldn't build Perseverance and send it to Mars, right?" Most people think there's a good chance that there might be Martians, but as I said, it's extremely difficult to show that's the case, and there might not be. I don't know. Favorite planet? Well, let's go to Elon Musk. Let's mention the other rocket engineer. So he wants to go to Mars. Might well get to Mars. That's the only other planet you could go to, actually, in our solar system, because Mercury is way too hot. Venus is horrendously hot, and 90 atmospheres pressure and sulfuric acid rain. It melts lead on the surface, right? So you're not going there. And the rest of them are made of gas, so you're not going there either. So Mars is the only place beyond Earth that we could feasibly ever go with planets. We could imagine perhaps going to some of the moons of Jupiter and Saturn. In the far future, that's much more difficult. At the moment, the thing that I'm working on, in some sense professionally, is with half a PhD student shared with someone, but also writing a book. It concerns black holes, and it concerns a very simple question that Stephen Hawking initially triggered and asked, which is what happens to the information contained in something that falls into a black hole. Does it disappear from the universe forever? Or when the black hole has evaporated away, which is Stephen's first great contribution to physics, was to show that black holes have a temperature and evaporate. And so ultimately the black hole will be gone, and all that will be left is Hawking radiation. And there are very profound questions. His initial calculation suggested that the radiation is what's called thermal, which means technically that it contains no information at all about anything that fell in. If you burn a book, then in principle, if you collect all the ashes and all the gas and everything from the book, in principle you could reconstruct the book. So the information has not been destroyed. It's still contained in the radiation and the ashes that have left. But the problem with black holes, according to Stephen's initial calculation, and really naively according to the production process, the production mechanism is they radiate because they disrupt. So the vacuum, the so-called quantum vacuum, empty space, is really disrupted by the presence of an event horizon. So it's one way you can think about it. So really the radiation is really a property of the event horizon. But if you throw a book into a black hole, then it goes across the event horizon without drama, according to Einstein, free falls in, and ultimately meets the end of time, the singularity in the middle of the black hole. So it goes to the end of time, let's put it that way. So it's kind of gone. From the perspective of the book, it went to the end of time. But the radiation is being produced independently of the book, right? No, it's not like being setting on fire. And yet, everything we know about physics suggests that the information should be preserved. So you shouldn't destroy information in any physical process in the universe. So a great challenge raised in the 70s and 80s, which has been solved, I would say, in the last 2 or 3 years to an extent, is that challenge. Does the information get destroyed? We think it doesn't. We think it comes out and it's encoded in the Hawking radiation. That's leading us to a very profound reassessment of the nature of space and time and what they are. So we're now strongly of the view, I think most people, that space and time emerge from a deeper theory, which is quantum mechanics ultimately. It doesn't have space and time in it. But that's all coming from the study of the very simple question of does something that goes into a black hole come out, basically, again, in the future. And so that's quantum gravity. And we need quantum gravity to understand, if we're ever going to speak with any authority about the origin of the universe, if it had one, or to understand what was happening very close to the Big Bang, or before the Big Bang, whichever way you want to look at it, then we need that theory. So I'd like to know what that theory is. And part of that's just because I'm so interested in black holes, that fascinated in the developments. It's really weird that just to give you a flavour, not only now are we pretty sure, I think everyone's pretty convinced that the black hole evolution does not destroy information. But if you say, well, how is it encoded in the Hawking radiation in the far future? It's encoded redundantly, it turns out. So in a manner that seems to be similar to the way that we encode information in quantum computers in order to prevent errors in the memory of quantum computers, called the quantum error correcting code. So it seems that there's put it this way, it seems like the fundamental view of the universe, the fundamentals of the universe are information theoretic rather than physical. John Wheeler, great physicist, said way back decades ago, he had this thing called it from bit, which is that reality comes from bits. It's all bits. And that does seem to be the lesson from the study of black holes. So the old answer of what happens if you jump into a black hole is you go to the end of time. That's this pure Einstein, right? You get spaghettified on your way to the end of time, which means you get stretched infinitely, actually, and then squashed, and you get dissociated into a train of atoms, and then everything goes to the end of time. Now, as of 2019, I would say, we think that if you think of yourself as information, so if you think of think very 2022, right? Let's say you burn a book. So burn a book and collect everything that comes out of the book, all the ashes and all the gas and everything. Then in principle, you can reconstruct the book. Not in practice, right? But you can imagine if you collect every single thing and measure it, in principle, you can reconstruct the book. Information is conserved in all of physics, which means that, so basically, if you can measure everything perfectly, you can predict what happened in the past and what's going to happen in the future. It's called determinism, that, right? So the old picture of black holes is that they seem like they destroy information. You can just kind of see it goes to the end of time, right? It's gone. And then they evaporate away. And it seemed that there was no way, even if you gathered all the Hawking radiation that had come off for trillions of years, there's no way you could reconstruct what went in. So therefore, if you jumped into a black hole, you'd be erased from the universe. But that breaks pretty much every law of physics, right? Things don't erase information. They scramble it up, make it difficult to read, but they don't destroy it. But now we think, actually, no, even black holes don't destroy information. So it turns out that now we think, and this is very 2022 papers, right? If you jumped into a black hole, then we do think that if a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in. So actually, in some sense, you come out. Stephen Hawking had a bet, and it was, I can't remember, I think it was the 90s when he conceded the bet. It might have been the late 80s. But so he had a bet, and the bet was that Stephen's calculation initially from the 70s said that black holes destroy information. And so he thought that was true for a long time. And he had a bet with John Preskill. And it turned out that the bet was a set of encyclopedias. So whoever lost the bet would have to give the other one a set of encyclopedias. And John Preskill asked for baseball encyclopedias. And because of some work by someone called Maldacena, actually, ultimately, Stephen said, no, they don't destroy information. The information comes out. It's conserved. So he conceded the bet and gave John Preskill the encyclopedias. He said, what I should have done is I should have burnt the encyclopedias and given him the ashes, because all the information's still there. So it was, yeah. So what that's saying is that the theory that you can write the gravitational theory, so the theory of our worlds, right, general relativity and so on, You can write it completely in terms of a theory encoded on the boundary surrounding the space. And so that's the holographic principle. That's the hologram, which is that you can encode a 3D object in a 2D piece of film completely. So it does seem that there's at least a dual description of our universe on a surface somehow surrounding the universe. Whatever that means, it's very vague. It was first done in what's called ADS space, which does have a well-defined boundary, and now it's not. And so, but it, broadly speaking, it comes from, and there's one way of describing it which comes way back. The hints of it were way back with Jacob Bekenstein, who worked with Hawking a long time ago. And he, long ago, in the 70s, realised that the information, how much information is contained in a black hole? Ask that question. And it's equal to up to a factor of a quarter. But we can forget the quarter. It was a misdefinition of something. So let's say it's equal to the surface area of the event horizon measured in square Planck units. So Planck unit is a fundamental length scale in the universe. So for some reason, the information content of a black hole is proportional to the surface area of the event horizon. And you can imagine that's like saying, how much information can you fit into a library? Well, you would think it was to do with the volume of the library. How many books can you fit inside the library? But it turns out that it's as if you can only paper the walls of the library with the pages of the books. It's almost as if the interior doesn't exist in some description. And that's again what black holes have been pointing us towards. It's very weird that would be the case. There's a fundamental link between the surface area of a space and the information content it is capable of storing. That's quantum gravity then, somehow. Nobody knows how, but it's quantum gravity. It's funny because when you hear the experts talk about it, and I've talked to some of the real experts, and they're often reluctant to put it into words. It's quite well defined mathematically, but actually what it actually means, what the interpretation is not agreed upon. And so many of the real experts in the field sort of rightly, I think, shy away from attempting to... You'll hear people talk about wormholes connecting the interior of the black hole to the Hawking radiation in the far future. But actually, when you try and pin people down, they're not... It's more like they look like wormholes in the maths, but it's not clear what that... Does it really mean? There's a wormholes opening up? Does it mean that? I think this is the cutting edge, but it's fascinating. What everyone agrees upon is that we're getting a glimpse of a deeper structure of space and time. Everyone agrees on that. So there's something else below it, and below time, underneath this thing we call time and space, there's something else. There's a great analogy actually. It's really similar when I look at the history. If you go back to the 19th century in thermodynamics, which is the study of temperature and pressure and volume and entropy, these things, what they were telling us, although we didn't know it initially, was that matter is made of smaller building blocks. So they were actually telling us that there is a statistical theory of small things underlying these things that we measure, temperature, and we can calculate, like entropy, things like that. People wanted to do it to build better steam engines, so that's what they were doing. But it was telling us about atoms and molecules, but we didn't know that. And it's actually only to the late 19th, early 20th century when you see that connection is made. So it was a signal there was something below, some deeper structure. And now we have the temperature of a black hole, the entropy of a black hole, the laws of thermodynamics for black holes. And what they're really telling us, I think, is that gravity is a statistical theory. So space-time is made of something else. So we're seeing the average behavior of something else, and we're calling that gravity and space and time, in the same way that we call the average motion of molecules temperature and entropy and so on. Yeah, so we're approximating. But it's what we do in our lives. We don't think about atoms. We think there's a glass of water here, so we say, what's the temperature of it? temperature is not a fundamental thing. It's a thing that tells us about it's a parameter that tells us how ultimately how the molecules are distributed amongst the available energy levels, which is quantum mechanics, in this structure. So it's telling us about the distribution of energy in the structure and the structure itself, and how many different levels of energy it can have, all sorts of stuff, which is deep. But ultimately out of it comes this thing, temperature. Also, you can interpret it as the average energy of the things moving around. There's a thing called the thermodynamic arrow of time, which is really the statement that the asymmetry between the past and the future in the universe is to do with the special state of the Big Bang. So Sean Carroll, I don't know if you had Sean on the show, but he has a really nice analogy where he says that it's like there's no up and down in space. But if you put a big thing there, like the Earth, then there's an up and down. You break the symmetry, right? It's the same with time. So in one way of thinking about time is that because of this special configuration in the past, that determines the difference between the past and the future. But I've not seen anyone say that dark energy, relate dark energy to that. You probably could somehow in the thermodynamic kind of argument. But then that's very different. That's our experience of time, the thermodynamic arrow. That's different from the quantum gravity question. There's in the Drake equation, which is Frank Drake wrote down. It wasn't to try to estimate the number of civilizations really. It was to try and focus your mind on what the variables are, how you should think about it. But at the end of that, the way that he wrote it, there's an L, the letter L, which is the length of time a civilization will be broadcasting or contactable through radio waves. And, you can set that. I mean, we've been around in that form, which is with radio telescopes. I like it that astronomers define civilization as when did you get a radio telescope? Then you're civilized. And, it's less than 100 years. So we've only been, that L for us, is the contactable lifetime of civilization. It is, 100 years or so for us. We could have gone. You think about the Cuban Missile Crisis, for example. That could have been 20 years for us, 50 years. We're still in that position. How long is L? How long is the lifetime of civilization once it acquires nuclear weapons, for example, which it will? How long does your civilization manage that? It's not clear. We're doing the experiment, and we've dodged it a few times. Climate challenge, all the things that you are inevitably challenged with as you industrialize. Oppenheimer thought about this a lot because he, on the Manhattan Project, he'd felt himself responsible for creating the bomb. You can look at it many ways. You can say that he shortened the war in the Pacific, or you can say that he invented this thing that we don't have the wisdom to control. He felt the latter, I think. He was very worried about what he'd done. And, he was surprised. He just strongly felt, and he might still be right, that we didn't have the wisdom to control the knowledge that we've acquired through science. So it could be the case. So that could be another answer. So the great silence that people call the Fermi paradox, the fact there's nobody seems to be there, might just be because we are fundamentally idiots. Intelligent beings are fundamentally just dumb. Why did I become interested in astronomy? Because I had an emotional reaction to the night sky. That's what it was when I was younger, 5, 6, 7 years old. I just found it, powerful, romantic, fascinating thing. And so I think at the heart of all science is just a desire to know, which is an emotional reaction. If you're a biologist, you might get fascinated by the way that the ants are making a path across your garden or something like that, but it's interesting, not because you're initially interested in the detail. You've just found something interesting that you want to understand. And so I think that at the heart of science, at the base of science, is an emotional there's an emotional seed which is that you are just interested and fascinated by something. And then again, Feynman said I don't even need to quote Feynman. I can do my version of it. So I made a series years ago called Wonders of Life, which was a physicist view of biology. Really, it was inspired by a book that Schrödinger wrote. So Schrödinger's cat fame, quantum mechanics, called What is Life, back in the 1940s, where he really laid the foundations for a lot of modern biology, in particular DNA. Right, it was and also bringing thermodynamics into biology. It's a very profound book. And so I made a series like that, and I realised that if you look at, for example, a blade of grass, right? So go out everyone can go outside now after listening to this and find a blade of grass. And actually, the whole history of life on Earth is written into that blade of grass. Like, we share a common ancestor with that blade of grass. Back, not actually hugely long ago, actually, the eukaryotic cells, whenever that was, let's say 2 billion years ago. It's quite a long time, but but there's a single origin to life. The last universal common ancestor called Nuka, which is back there about 3.8 billion years ago, we think. So, in what you should see there is an organism that's essentially four-dimensional, right? The structure of it cannot be understood without understanding the history of a planet, and that's what science does for you. It makes it even more beautiful. So it's a beautiful thing in itself. But the more you know about how it got there and what it represents and its story, the more beautiful it becomes. So that's emotional. It's an emotional reaction to the thing. So you should have an emotional reaction to a blade of grass because it encodes the history of a planet. Sagan said it. There's a beautiful, I think it's in Billions and Billions. I can't remember which book it's in, but he writes about when he was a kid and he looked at the stars and he said, "What are those things?" And someone said to him, "They're just lights in the sky, kid." So he went to a library. His mum took him to a library and he got a book and he found out that they were other worlds. And he thought, there were other worlds. And now we know that they've all got planets, right? To a good approximation, all of them have planetary systems. So every point of light you see in the night sky has got planets. So there's a solar system there. And then you can dream about those other worlds. Are they Earth-like? What are they like? Super Jupiter type things? What's up there? So the more you know, the moment you know they're not just lights in the sky, they're infinitely more magical. And that's true. It's always the case. That the more knowledge you acquire, the more magical something becomes. Yeah, it's quite a machine, the web. And it's got a lot of purposes, but one of them is that it can see into what's called the infrared, which is longer wavelengths. And the reason we're interested in long wavelengths is because the light from very objects that were forming very early on in the history of the universe, so from which the light has taken up well over 13 billion years to reach us, those things, the light's been stretched by the expansion of the universe. And it's been stretched so much for the earliest stars that Hubble, which is our most powerful space telescope other than the Webb, can't see it because it's gone into outside of its visual range. So the Webb is going to be able to see the formation of the first stars in galaxies, so it can see further back in time into what we call the dawn, right? Just the edge of the cosmic dark ages before the dawn. So that's just one of the things. The other thing is it's powerful enough to look at planetary atmospheres beyond the solar system, exoplanets, to start looking at them really seriously, to say what's in them. Do they have carbon dioxide or nitrogen? If you saw oxygen, high concentration, I doubt it, but if we did, you'd see photosynthesis in action, most likely. So you'd discover life. One of my great heroes, Richard Feynman, wrote a great essay called The Value of Science in 1955, in which he reflected on what's the most valuable thing that the study of nature teaches us and how that can be used in other fields of human endeavour. And the most important thing, he said, was that nature very often tells you that you are wrong, right? So whatever your opinion is and however important you are, If your view of nature is wrong, then nature will ultimately tell you, and you have to accept it. So he said that scientists have a great deal of experience with being wrong, and it's a delightful experience because you've learned something. So the way you thought the world works turns out not to be, and so you know something then you've learned something, so you understand more. So he called science a satisfactory philosophy of ignorance. But his point was that you can take that delight in being wrong, the fact that you don't know, because obviously in order to do research, you have to first accept that you don't know, otherwise you wouldn't do research. That's the way that we have built our civilization. But you can take that idea and transplant it to other fields of endeavour, such as politics, for example. So imagine that our politicians started every speech by saying, well, of course, I could be wrong here. Of course, I don't know. It's really complicated. But the best of our ability at the moment, I think this is a way to go. And if we make some observations and it's not gone quite right, then we'll just change a bit and we'll fiddle around and we'll do something else. So we'll increase taxes, or we'll decrease taxes, or we'll change the way that we target environmental emissions, or something, anything, whatever it is. Imagine if they said that, then we would live in a profoundly better world. Right? What we have are a bunch of people who are certain. And I don't get involved in politics so much, but the one piece of advice I always give people is, if the person you're going to vote for sounds really sure, then do not vote for them. They're either dumb or disingenuous, or some combination of the two, because they should know that it's really hard to run a country. In fact, Feynman said in that essay that democracy is a manifestation of that. It's the acceptance that we don't know how to run a country. So what we do is we change everything every 4 years. Why would you do that? If you think you know how to do it, you wouldn't do it, right? But of course, so the pendulum swings backwards and forwards, and that is, as Feynman said, and Oppenheimer said this as well, the great Robert Oppenheimer, that swing, when you see the swing, then what you're seeing is your freedom. Right? You're seeing the fact that this bunch of people thinks this and this, and we'll try them all. We'll try all these different ways. So it's the manifestation of your freedom when people vote, and it goes against you, and it goes towards you, and it goes against your beliefs, and that's just great. The moment it stops doing that is the moment that you're no longer free. And we've made a big mistake, as Feynman said, because every time we think we know how to do it, then we make a mess of it. You can see that in history, right? The more certain the leaders are, the bigger mess they make. So I did an event with Kip Thorne just a while ago. We did a conversation together, and Kip knew him very well. And he said that, so Feynman was always very dismissive of philosophy, for example, the philosophy of science. He said, what did he say? He said, I think it was Feynman who said that the philosophy is as useful to scientists as ornithology is to birds. But, however, Kip said that he thinks that Feynman's book, The Character of Physical Law, is the best work of the philosophy of science ever written. And he said that to Feynman once. He took it into his office and said that, and Feynman threw him out of his office. But the thing about Feynman is that if you read The Value of Science, which you can just get online, right? You just type Feynman, The Value of Science, it comes up. It's the most beautifully written, eloquent, thoughtful piece of writing you could ever imagine. It's absolutely, it's profound and brilliant. And I think Feynman sort of played on this kind of idea that he was kind of a guy from Far Rockaway, New York, and he was kind of a bit tough, and the way that he lectured often was to, use that kind of slang, that language. He was very, very down to earth, but he was capable of writing this most tremendously deep and insightful prose, which he could do. So he's a very multifaceted individual, but first of all, a brilliant scientist. The way I look at life is that it's the most important phenomenon that exists in the universe. Without life, the universe is by definition meaningless. It's clearly that meaning enters the universe with consciousness, and consciousness is a property of living things. And so without living things, there's no meaning. So I think that let's flip it round. If this is the only planet in the Milky Way galaxy that currently hosts an intelligent civilization, then it's the only island of meaning in a sea of 400 billion stars. And therefore, we have a tremendous responsibility to protect this island of meaning. If we mess it up, we will be responsible, if that's the case, for annihilating meaning, perhaps forever, in a galaxy. So I think life's important.